Hello, everybody, and welcome to titrations. This is our second last lesson of the course. I can't believe it. Holy smokes. Super proud and impressed of all of you guys who stuck with me the whole way through this online learning experience. It has not been easy for you, I'm sure, and it has not been easy for me as a teacher to be delivering lessons this way every day instead of being in the classroom with you guys. So congratulations and thanks for all your work so far of getting through the course under these challenging conditions. So I was going to tell you a quick story before we get going on titrations. I was out riding my bike on the Red Deer River trails yesterday, and I was coming across the bridge over by Heritage Ranch, and I saw a murder. I know, shocking. I actually saw a murder. I heard all this noise in the trees. I was with my daughter, and we looked over, and sure enough, there it was. A murder. 20 crows in a tree tormenting an owl. And you're thinking, wait a minute, he said murder. Well, that's the term for a large group of crows. It's a murder. And they were literally tormenting this great horned owl. And then he took off, or she took off, and all the crows followed it, flew down the river to the next big tree, landed, and they were just at that owl. It was crazy. I don't know what their point was. They were literally harassing it, I guess trying to get it to move out of their territory. Pretty interesting, though, to see something like that. One of the benefits of getting outside and being active, you get to see these crazy scenes in nature. So hopefully you guys are all getting out. The weather's been beautiful lately, despite the rains. When it's not raining, it tends to be pretty sunny and lovely. So I always find it's a nice way to charge my batteries, get outside and have a little bit of activity. Okay, titrations. Now, sadly, this is one of my favorite topics at school because there's lots of hands-on labs, and we don't get to do that, which is unfortunate. So I've got a video I'm going to show you as well that goes through the technique, but what is a titration all about? So you guys have done solution stoichiometry, and titrations are the methods or the procedure that you use to get the values you need to do solution stoichiometry. So you're usually adding one solution to another, and your goal is to try and determine the concentration of one of the two solutions. So you have a known concentration and an unknown concentration, and you use some pretty specialized glassware to do that. And that's this big glass tube that you see here. I'm just going to outline it a little bit. It's called a burette, and it has a valve at the bottom and a very small little point. And the idea is that you can add drop by drop the chemical in the burette to the chemical that's in the beaker. So usually it's an acid-base neutralization. So we might have an acid in the burette and a base in the beaker, and we're trying to find out the concentration, of the material in the beaker. So that's the very basic idea behind it. And it takes a lot of skill. As you can see here, this person's using their two hands to try and operate the valve and add drop by drop the acid to the base. And the way the reaction works is you have an indicator that changes color, and that's when you know when to stop. So there's a lot going on in an acid-base titration, and so that's what we're going to be looking at today. We're going to go through the theory, the methods, and then the math behind this stoichiometry. A couple terms for you to fill in on your notes if you printed that off. So the title is Standardizing Titrant Solutions. So in chemistry, when we have a solution of an exact concentration, we call it a standard solution. So it's a known exact concentration. For example, we could say that the concentration of H2SO4 is 1.43 moles per liter. So that is a very exact concentration to the second decimal place. A primary standard is a chemical that you can get at a high purity, so it's usually a solid. So it has a mass that you can measure with a high accuracy on our scales. So we have scales that will measure to the second decimal place. So you take a primary standard, and from that you can build a solution. So we use primary standards to build a standard solution of an exact known concentration. And sometimes to find that concentration, we standardize the solution. So finding the concentration of a solution after it has been prepared. So we use a primary standard to build this solution, and then we standardize it. And when we're done, hopefully we have an exact concentration, and that's where titrations come in. Okay, so here's the setup, and you have this picture in your notes. So when you're doing a titration in the lab, you have a funnel sitting on the burette that allows you to fill the burette. And usually you put your known concentration in the burette. So for example, 1.47 moles per liter of H2SO4 if we were going to put an acid in there. So we know its concentration, and then in the Erlenmeyer flask would be your base in this example, and it has an unknown concentration. So our goal is to try and figure out what is the concentration of our base if we know the concentration of our acid. And you do that by adding drop by drop the acid to the base. And what kind of a reaction is that when an acid reacts with a base? Neutralization. And the goal is to neutralize all of the base in the Erlenmeyer flask. Neutralization. Stop when base neutralized. How will you know when to stop? The indicator changes color. I'm kind of jumping all over the place here. I usually like to demonstrate this in the class and talk about it. So we'll have an indicator in here. I'll put a color in here. Might start off pink and then it changes to green when it's neutralized. So that's when we would stop. Okay, I'm going to show you a quick little video that shows the sort of technique of this. It's just like 2 minutes long.
It is not necessary to dry the flask. Record your starting volume. It is important.
Oh my gosh, what did I do?
Grammarly does more than catch errors. With Grammarly, you can find really good.
Okay, sorry.
Read the volume on the burette. First, note that the liquid forms a concave meniscus because the water pulls itself up the side walls of the glass. You should read the volume from the bottom of the meniscus at eye level. Secondly, it is important to read your volume to the correct number of significant figures. This burette indicates volume to the nearest 0.1 milliliters. With any graduated glassware, record the volume to one additional decimal place beyond the smallest graduation. In this case, record the volume to the nearest hundredth of a milliliter, estimating the final place. Use the volumetric pipette to transfer the analyte to the flask. Add a few drops of indicator to the flask and swirl. Place the flask under the tip of the burette. Record this volume. Placing a piece of white paper under the Erlenmeyer flask may make it easier to detect the color change. Operating the burette requires 2 hands. One hand turns the stopcock, while the other hand swirls the flask. Practice turning the stopcock a few times to familiarize yourself with how quickly the flow starts and stops. It is common laboratory practice that the first titration is an estimate. Open up the stopcock and allow the titrant to enter the flask quickly. Continuously swirl the flask. As the volume of titrant in the flask increases, the color of the indicator appears, then disappears as you swirl. When the analyte becomes a colored solution, close the stopcock. Record the final volume of the burette. Subtract the initial volume from this final volume to get the estimated volume of titrant needed for this titration. Knowing the volume that is a little...
Okay, so we'll stop that one there. So that just sort of gives you an overview of the procedure of how you use the burette to add. And in that example, they were adding a base to an acid. And so it's the opposite of this one, but it doesn't matter, same idea. So the base to the acid, and when the indicator changed color, they stopped. So what they were filling in was a table, a chart. And the idea is in a titration, you actually do 3 or 4 experiments, 3 or 4 trials. And the first one is usually an estimate. And it's done quickly, and it's just to get you a rough idea of the volume that you need to add to neutralize your unknown. So in this one, we're looking for what is the concentration of acetic acid, and there should be a space there. So we have 10 mils of acetic acid. So what is the concentration of the acetic acid? So in this example, oh my gosh, that is the worst Erlenmeyer flask I've ever drawn in my life. Okay, in this example, the acid, 10 milliliters, is sitting in the Erlenmeyer flask, and the base is sitting in the burette, and the base is NaOH. And it's 1.25 moles per liter. So we know the concentration of the base, the NaOH. We're going to add it drop by drop, and we're going to get the volume. So we have the concentration. When we record when we start, 49.9 mils, and we record when we finish, 43 mils. So our difference is 6.9 milliliters. And it turned pink. Okay, so now we have a volume, 6.9 milliliters. And we have a volume of acid. Okay, so here's the big moment. Using stoichiometry, we can do solution stoich on this because we have a balanced chemical equation. Sodium hydroxide reacts with acetic acid to produce water and sodium acetate. I'm going to skip my states just to roll along on the math. Okay, so solution stoich. We're looking for the concentration of the acid. So concentration of CH3COOH. So we need concentration and volume of one chemical. And I should tell you that when I was marking your last assignment, the most common mistake students made is they didn't know which volume to multiply by a given concentration. So in this example, we have the concentration of NaOH, so we would multiply it by the volume of NaOH. Now, here's the other big idea. We're not going to use that 6.9 mils because that was just an estimate. We're going to do this experiment 3 more times to see if we can be a little more precise on our drops and get the reaction to stop exactly at completion. When it is 100% complete, no more, no less, we're going to stop it. So we do the experiment a second time, and we get a volume of 6.5. We do it a third time, 6.6, and a fourth time, 6.4. And all of them are turning pink. Light pink would be the best case scenario. That means you caught it just in time. So now we're going to take the average of those three. So 6.5 plus 6.6 plus 6.4 divided by 3 is 6.5 milliliters. Now that volume, we're more confident in it. That is exactly the volume that we are hoping to get for our accuracy. So that's the one we'll use for our stoich. So cross out the 6.9, and in reality, it's 6.5. Okay, now we can do our stoichiometry to figure out the concentration of the acid. So in solution stoich, you always start with concentration and volume of the substance you know, which is NaOH. So we have 6.5 mils of NaOH times its concentration, 1.25 moles per liter. Okay, now that's our NaOH, but we need to turn it into acetic acid, and this is an easy one. It's a 1-to-1 ratio, so the one we're looking for on top. And the chemical we're going to cancel out on the bottom. And if you want, you can put moles in here. 1 mole, 1 mole. They cancel out, so it doesn't really matter. Okay, the NaOH cancels out. If we want, we could cancel out the liters and be left with millimoles. I'm just going to leave the milliliters for now. So I have the millimoles of acetic acid, but we want the concentration or moles per liter. So the last thing we have to do is divide it by the volume of acetic acid, 10 mil. The milliliters cancel out, and we are left with moles per liter of acetic acid, which is what we're looking for, concentration of acetic acid. So you plug that into your calculator and you get 0.8125 moles per liter, and 2 sig digs, 0.81 moles per liter. So that's the math, the stoich behind the titration, and the things you have to remember. There are the title of the titration table always gives you a volume and a concentration. And then when you take your last 3 trials and you get the average volume average, that's your third piece of data. So 1, 2, 3. We now have our 3 numbers that we need to do the stoichiometry. So that's the idea behind these tables and how they work to help you calculate the concentration of an acid or a base. So we're going to try one more of these questions. Okay, so here's a second one. This one's a little more challenging. It's got a little more going on. Let's take a look at it. Determine the concentration of hydrochloric acid. Okay, so we're looking for concentration of HCl. Okay, and we're doing a titration by making 1.59 grams of sodium carbonate dissolved in 100 milliliter solution. Okay, so the first thing we need to do is they don't tell us the concentration of sodium carbonate in the title. They're making us figure it out. So this one has an extra step. So concentration of Na2CO3. So we need the moles per liter. And they're giving us the grams dissolved in 100 milliliters. So to get moles, we're going to need molar mass of Na2CO3, which is 105.99 grams per mole. Just going to write that up here. Molar mass of Na2CO3, 105.99 grams per mole. Okay, so moles per liter of Na2CO3. There's my moles over 105.99 grams. Let's cancel out the grams. 1.59 grams. And I need it over liters, which I can just put right here. And 100 milliliters is 0.1000 liters. Another mistake a few people were making is they take 100.0 mil and they turn it into 0.1 liters and call it 1 sig dig. That's wrong. This number has 4 sig digs. The conversion also needs 4 sig digs. 1, 2, 3, 4 sig digs. Okay, so grams cancel out and we get the moles per liter. And that works out to be 0.150 moles per liter. 3 sig digs from our limiter. Okay, so now we have the concentration of Na2CO3, 0.150 moles per liter. So we have 10 milliliters of Na2CO3. We have its concentration, and we have the volume of the acid. So we have our 3 numbers. Now, remember the first trial is an estimate, and you can see that it's 13.1. That's too high, so we cross it out. These are the 3 we're interested in, 12.7, 12.8, 12.8. So let's get the average volume of those 3. 12.7 mil plus 12.8 mil plus 12.8 mil divided by 3, and we get an average of 12.76 repeating. Okay, so there's our volume of acid. So now we're done with the table. We're ready to do our stoichiometry. So we need that balanced equation, and it is Na2CO3 reacting with HCl. Na2CO3 reacting with HCl to produce NaCl and H2CO3. This is a tricky one. We're going to need a 2 in front of there and a 2 in front of there. 2Na, 2Na, 2Cl, 2Cl, and a CO3, a CO3, and 2 H's, 2 H's. We're balanced. Everything is aqueous in here. So there's our balanced equation. Now we can do the stoichiometry, and we are looking for the concentration of HCl. There's a lot going on here in these problems. We finished this course with some of the hardest stuff. Okay. The concentration of acids. So we'll pause for a second here and think about this. Solution stoich. Start with the volume and concentration that we know of the one chemical, and we know we have 10 milliliter samples of Na2CO3, and we now know its concentration is 0.150 moles per liter. So there's our concentration and volume to start. 0.150 moles per liter of Na2CO3 times its volume, 10 milliliters. Okay. So that gives us the millimoles of Na2CO3. We're looking for acid, so we're going to write acid on top. 2 HCl from our balanced equation for every 1 Na2CO3. Okay, last step, that gives us the moles. We need the moles per liter, and it's the acid we're interested in. And the average volume of the acid, the HCl, is 12.76, repeating. We're carrying all the digits through because it's an intermediate step. Okay, so there's all the math. Crunch it all into your calculator and you should get concentration is 0.235 moles per liter. 3 sig digs is our limiter. So we've determined the concentration of HCl by using the volume of HCl and the concentration and volume of the base, and our molar ratio to convert base to acid. So it's solution stoich. Okay, so that is acid-base titrations. This is a summary of the technique, things that I just talked about. So titrations are a technique, and it allows you to add a very carefully measured volume of solution. We call it the titrant from the burette into a fixed volume. And for Chem 20, the fixed volume is always 10 milliliters, and that would be in the Erlenmeyer flask. Okay. So the titrant sits in the burette and gets added to an Erlenmeyer flask that has exactly 10 milliliters, and the concentration is unknown in the Erlenmeyer flask. It says the concentration of one reactant must be accurately known, and that's this one. Concentration is exact in the burette. The titrant, we know its concentration. We titrate until the equivalence point is reached where all of the acid has reacted with all of the base. And then we stop because there's a change in a property, which for you guys is always a color change of the indicator. When it changes color, you stop. And as I said, we'll do several trials till we get 3 in a row where the values are really close, within 0.2 of each other. And let's go back and just check that. Were these all within 0.2? Yeah, they were all within 0.1, 12.7, 12.8, 12.8. How about our first example? How close were the volumes? Yeah, they were all within 0.2, 6.4, 6.6, 6.5. So we went from 6.4 all the way up to 6.6, a difference of 0.2. This one's outside of that. It's missing the mark by 0.64 to 6.9. It's out by 0.5, which is too much. So 3 trials that are with a maximum range of 0.2. So we met all those criteria for our titration to be able to do the stoichiometry calculation using that average volume. That's a lot of info, I know. Okay, practice makes perfect. There is a titration worksheet in your study guide, and I will post the answer key online to that. And this one takes a little bit of time. There's a bit of work to doing these, but once you've done 1 or 2 of them, you get the pattern and they're not too bad. Okay, so I'll have an answer key to that, and I'll put that exact page number in the lesson for you. Okay, hopefully you have a pretty good idea of titrations. I'm going to put a link to that video and the second link from Professor Dave, who also talks a little bit about acid-base titrations if you want a little more information to help you understand how they work.